Okay, thank you very much for the introduction and the opportunity to talk. So hopefully you can all see my slides, and I'm going to give you an overview of some of the work that we've been doing over the last 5+ years on modeling a few different aspects of surface-enhanced Raman scattering using the ADF package. So all the stuff that I'm going to show you have either been directly implemented into the ADF program package or uses tools for the ADF package to do these simulations. And so one of the reasons that we're interested in surface-enhanced Raman scattering is that it allows us to understand molecules at interfaces. So we were able to get signatures of molecules in diverse environments. And there's lots of different types of applications where you would care that I sort of just listed a few of these. And so I'm going to try and explain sort of some of the underlying principles of surface-enhanced Raman scattering and how we can use electronic structured theory to model them and gain insights into them. So it's going to be a little more on sort of the theory with a few applications of each of these theory elements. And so you got to get a sense of what this is. And so there's sort of the simplest explanation of this concept of surface-enhanced spectroscopy, or specifically surface-enhanced Raman spectroscopy, is that the light excite these collective excitations, these called plasmon excitations, and these particles on structured nanoparticles. So these are typically either colloidal particles or fabricated particles, substrates that has dimensions of a few tens of nanometers down to a few nanometers. And these plasmon excitations generates a strong enhanced local field at the surface of these particles. And the spectroscopy sort of uses the enhanced local field to enhance any sort of observable optical properties of these molecules sitting on the surface. And the ones that we're particularly interested in is Raman scattering. So this will give you vibrational frequencies and a spectrum, right, of down to single molecules sitting on this. So you can get enhancement of the sort of the normally weak Raman scattering of 1,000,000-fold to 10 to the 10th, which will allow you under some conditions to detect single molecules that sits on these surfaces, okay, which means this is a very sensitive technique. So you can have high resolution, but because it's a vibrational spectroscopy, you also have high sensitivity. And so what we want to try is some aspects of actually modeling this. So I'm gonna talk about 3 different aspects of modeling SIRS that we've done, implemented in the ADF program, or again uses features from the ADF. And the first one has to understand chemical effects and SIRS, so sort of the direct coupling between the molecule, these metal nanoparticles, and how we can understand the enhancement mechanism in SIRS. The second thing is how we can incorporate sort of the environment that these molecules sits on the nanoparticles. We're going to talk about how solvent effects actually modulates the Raman scattering of this. I'm going to finally show an example of where we can use simulations to model sort of images of individual vibrations on surfaces, which is going to be in the last part. Sort of first one that we're going to talk about is a little bit on sort of the enhancement mechanism and surface-enhanced Raman scattering. So all the way at the left side, we have normal Raman scattering, right, where we're exciting, right, our system to basically a virtual level, and we decay down to an excited vibrational state. The difference between the incident and the scattered light, right, corresponds to the vibrational energy of the system, which is what we're measuring in a spectrum. Okay. And the enhancement mechanism from SIRS comes in sort of 2 parts. The most dominant part comes from this what's called the electromagnetic mechanism. And you can think of it as sort of using the local field that comes from these plasmon excitations to enhance both the absorption process of this photon as well as the scattered of this photon. Okay, and it turns out that one can show using rather simple models, okay, that the intensities that you have in surface-enhanced Raman scattering should scale with this local field to the fourth power. Okay, so which means a tenfold enhancement in the local field will lead to a 10 to the fourth enhancements of the Raman scattering. Okay? And these nanostructural nanostructures can lead to enhancements of the local field on the order of 10 all the way up to sometimes to 1,000 times. Okay, and so this leads to the predominant enhancement mechanisms seen in service. Okay, and so people have spent a lot of time sort of understanding and modeling this. Okay, the one thing that I'm particularly interested in is what happens when these molecules bind to the surface specifically, which changes the electronic structure and the geometry of these molecules onto the surface. Okay, and this is typically grouped into what we call the chemical mechanism, or CM. Okay, so this sort of groups everything in that you don't count for in this electromagnetic mechanism. And we tend to split this CM mechanism into 3 different distinct regions, which basically depends on which type of resonances you're looking at. If you don't have any sort of, your light is not in resonance with anything, we typically call it CHEM or CHEM. Okay? This corresponds to sort of the changes in the electronic structure of the molecules, but you're not hitting any electronic resonances in there. So that leads to a change in the energy levels of your system, and that leads to a change in the polarizability of the system, which leads to a change in the scattering. The other one is that you can get access to these charge transfer excitations. So this would be excitations from the metal surface into the molecule, or for the molecule into the metal surface. That can lead to also enhancements of the Raman scattering. These are what we call typically the CP. The other mechanism, which we're going to talk about, is called the resonance Raman scattering mechanism. So this is basically that you use your incident light, and instead of going to a virtual state, you go to a real state. Okay, the system. This leads to a resonance enhancement of the scattering. This is known for molecules away from surfaces as well, and can be used to generate very large Raman scattering signals as well. That is sort of indicative of the excited state of the molecule that you're exciting into. But onto the surface, because you're changing the energy levels of your system due to the coupling with the surface, you actually change this process here. So sometimes you can make it favorable or less favorable onto the surface, which means you need to understand how these things are on the surface. Okay, and so the collective things of both these electromagnetic and chemical mechanisms is what you observe from an experimental point of view. And what we would like to have is theories that can explain all of these mechanisms. Right? And so in principle, we can do this using electronic structure theory. Okay, so we treat molecules sitting on metal nanoparticles, okay, and then calculating the response of the whole systems. But we would like to find models of sort of understanding each of these different mechanisms. Okay, and so what we've done is develop what I'm going to call a first principle Raman. So this is going to take the results that you would generate from TD-DFT calculating using the standard approach that would be in ADF, and we partitions it into contributions that belongs to individual atoms and individual bonds. Okay? So I'm going to explain a little bit on how we do this. Okay? So the central quantity that we want to look at is the polarizability of the system. Okay? This is given again by the induced charge density of the system due to the external perturbation. And that external perturbation, we can use Hirschfeld partitioning to split it into atomic contributions. And so this is what's done in the first term, where we get a term that depends on an atom position, okay, relative to the coordinate system. And then we're going to have one that depends on the amount of electron density that you have on that atom, which is the charge of that system. Okay? Times again its points. Okay? And so this is sort of like a straightforward partitioning, okay, of the electron density in terms of densities. We just, in this case, we're just using the Hirschfeld partitioning, which is like a real space partitioning that's implemented in area. So we can do this for polarizabilities. The one problem with this way of doing the partitions is that the second term here depends on the charge, depends on the coordinate system that you have in the system. So if we move our system, we're going to get a different result, which means you have a origin dependence. Okay? And so to remove this, what we would like to do is rewrite this instead of relative charges in terms of charge flow between atoms. And so what we do is take these charges that are assigned, or these induced charges to each atoms, and then we assign them to charge flow between each atom. Okay? And so we can change these charge flows, okay, which now there's many more charge flows than there are charges. Okay, we do this by minimizing the Lagrangian, okay, that's given. This is basically a way of saying that we're going to force all the charge flow to go through bonds of the system. Okay, we define bonds using some sort of covalent radii of each of these atoms. Okay, and so this is basically the idea that was developed by Gargley in the low probe method for developing atomic polarizability. So we use a very similar to that. So that allows us to rewrite the polarizabilities in terms of a term that is for each atom, and a term that sort of depends on the distance between each atom. So that allows us to give a partitioning of the polarizabilities into atomic terms and bond terms. Okay, that's origin dependent. We can now connect this with the Raman scattering, which is the change in the polarizability with respect to a normal mode QK here. So that allows us to take the polarizabilities, which is split into these atomic polarizations or oscillating dipoles, and then this charge flow between these two atoms. Okay? And we can split it into terms that we're going to call a Raman atom or Raman bond. Okay, so this is again the oscillation of a dipole on each atom versus an oscillation between two atoms or bonds. Okay? And it turns out that the dominant term in all these corresponds to the Raman bond. Okay? So this is what we call the first principle Raman bond model. Okay, so it takes a TDFT calculation and then it automatically partitions it in to these atoms and bonds. Okay, that will sum up to the exact answer that you get. Okay. And so it's again, it's an analysis tool after you've run your TDFT simulation. Okay, the major advantage of this model, okay, is that since this is a real space partitioning in terms of atoms and bonds, we can connect that to where our physical space is. Okay, so we can group all the atoms and bonds that belong to the molecule, that belongs to a cluster, and sort of all bond interactions between these two sets of systems. Okay, and so this allows us to generate both these images, so like a visual representation of how the response due to the vibration and to the external perturbation is distributed in a molecule, but also in these different regions of that. And we can use this to define these these chemical mechanisms, electromagnetic mechanisms that happens in surface-enhanced Raman scattering. Okay? And so again, all the calculations to do the Hertz field partitioning is implemented into the ADF program. The way to generate the Raman bond model is at this point using a separate script to do this in post-processing. The nice thing about this Raman bond model is it allows you to explain sort of surface selection rules or mode-dependent enhancements, which is otherwise hard to explain for these models. So the one thing that I'm going to show you here is just examples for using a simple pyridine molecule interacting with a small metal cluster. These are typical model systems for studying surface-enhanced Raman scattering. Okay. Pyridine Raman spectrum and the free solution and the free molecule is dominated by these two ring breeding modes of the pyridine, this new 1 and new 12 mode. And in solution and for the free molecule, the intensities of these two modes are very similar. Okay. And so if you see the image on the right, you see the Raman bond model, okay, depiction of what happens in here. Okay. And so again, you can see the dominant term comes from the bonds. If they have the same color, they'll add up constructively. Okay, if they have opposite colors of blue or red, they'll add up constructively. If you sum up all the bonds, you will get the total response that you'll get. Okay, which means the larger of one color type bond you have, you will get to what is known as the Raman signal. Okay? And you can see for these two modes, although the vibrations changes the electron density differently, the mode patterns or the Raman bonds in these are very similar. Okay, which means you'd expect very similar enhancement. Okay? So each of these are scaled to the same level. But we then put it onto these metal clusters. We're fundamentally changing enhancement, okay? And specifically what we see is that the new 1 vibration in here becomes much, much larger than the new 12 mode. Okay? In this case, you can see that the factor is about 20 times stronger. Okay? So this comes from this chemical coupling to the surface. Okay? If you look at the Raman bond model, you can see what's actually changing is that the new 1 vibration allows for charge flow that drives into this metal nanoparticle and a very strong bond between the interface between the molecule and this nanoparticle. And so this is basically what we mean by this chemical mechanism. The ability of the vibrations of the molecule to drive this charge flow across the interface into the metal nanoparticle. And the more coherent this charge flow is, the larger your chemical enhancement mechanism is. And you can see due to the symmetry of these two, sort of the motion of these two different molecules, okay, the new 1 leads to this more coherent charge flow in the system, which leads to this larger enhancement mechanism, okay? So this allows us, right, to build a visual, right, and a quantitative way to explain why we actually get these large enhancements in surface-enhanced Raman scattering. So this was sort of one of those mechanisms. The implementation is done so that we can do it using damp response theory implemented in ADF. We can use this for a wide range of incident frequencies. So what I'm employing here is contributions to the Raman scattering as a function of incident frequency. Okay, so now I'm going through what we typically call the static limit out of 0, where we're not in resonance with any excitations in the system. And then we're going to drive it through the different types of excitations that we can have in the system. Okay? If you look at a large peak, where we get a very large enhancements around 3.5 eV, we see that this is typically excitations into the metal cluster of this, which drives largely these enhancements, or EM-like enhancement mechanisms. We can access charge transfer excitations around 2.2, okay, and we can go in and excite excitations in the molecule around 6 eV. So we can go in and pinpoint each of these excitations, and then we can decompose it into the response that corresponds to the molecular part, this intra part, or this cluster part, okay, and allow us to actually differentiate each of these different mechanisms that you see in service. And so it allow us to actually quantify for each of these different scenarios the contributions to the enhancement mechanism in here and figure out what it is. So when we're in the chemical mechanism, so far from any resonance in the system, we see that most of the enhancements is dominated by the molecular resonances, okay, also the molecular Raman bonds, plus, again, this charge transfer bonds into the system. As soon as you go and excite one of the charge transfer excitations in the system, the bond that lights up is the interfacial bond between the pyridine and the metal cluster. Okay. If you go on resonance with the sort of the excitations in the silver cluster, you see the network, okay, of Raman bond and the metal cluster lights up, and you can see that the largest contribution again comes from some of the Raman bonds in the cluster consistent with this electromagnetic mechanism. And finally, if we excite resonances inside the molecule, we can see again that the Raman bond for the molecule then becomes the dominant contribution in here. And so this Raman bond model allow us to take the TDDFT calculations, okay, and then map it on to each of these individual Raman mechanisms for how we can deal with this. So this is sort of an interpretation scheme that allow us to pull out the pieces of information that we care about from the full TDDFT calculation, where it otherwise would just give us the total spectrum in these cases. So this was sort of using full quantum mechanical calculations to look at the surface-enhanced Raman scattering and how we can interpret that. Okay. So the second part I'm going to look at here is how do we actually model much larger nanoparticles, and how do we model solvent effects in this. So one of the things that happens when you put a solvent molecule on here, so this case here, we're looking at a pyridine molecule sitting at the tip between 2 nanoparticles embedded in an aqueous solution. So the whole nanoparticle is embedded in water molecules, okay? And what we're comparing on the right is the absorption, the local field that comes if the nanoparticles were in vacuum versus in the bottom where we actually have it in solution. Okay, so what we actually see in these simulations is once you take into account the effect of the solvent, we need to do both a larger field, okay, as well as a confinement of the field on this, which means both of these things will affect the Raman scattering of the molecule that sits in this junction area. Okay, so we've been wanting to looking at solvent effects in this. So what we've done is extended the method that's called the discrete interaction model, quantum mechanical model that we've developed for a while, which is like a hybrid electrodynamic models where we treat on the response of the nanoparticles classically, okay, and then we treat the response of the molecule quantum mechanically, and then we couple these, okay. And so what we've done is extended this to also treat the solvent effects. Okay? And so the main thing that goes into solving this set of equations is sort of the coupling terms between the classical part and the QM part, which is given by this dim operator in here. This is typically what we call the image field effect. You can think of it sort of like a molecule nearing a metal surface. It induces an image charge in the other one, and this self-consistent polarization between this. This is largely what this image field takes into account, which means we have a polarization that comes from the metal. Okay, but we also now have included polarization that comes from the solvent molecule and that comes from the ground state charge distribution of all the solvent molecules in here that all perturbs our system. And then because we're doing surface-enhanced Raman scattering where we excite the plasma excitations, we also have to worry about this local field. So this is the additional contributions that we have added in here that comes from the metal. Okay, but there is also an induced polarization in the environment that comes from the solvent molecules that we've incorporated into these things. And all these things are solved self-consistently within the dim QM. Once we have solved this self-consistently, okay, then we can solve the damp response equations, okay, to get access to polarizabilities, and from the polarizabilities we can get access to Raman scattering. We can in principle generalize this to nonlinear responses, which we have done as well. But for now, I'm going to just focus on the linear response. Okay, so it means that we have to solve these set of damp linear response equations in the presence of these metal nanoparticles and solvent molecules in here, and these has to be solved self-consistently. So this has been implemented again inside the AO response module of AEF to provide an efficient solution of these systems in here. And one thing that's a little unique about the DIM-QM response properties that sort of, without going into too much details, okay, it can be understood from this quasi-unity derivatives. What this means is that once we calculate the total polarizability of the system, okay, we get all interactions between the molecule and the nanoparticle. So both what's induced from the molecule into the nanoparticle, but also what's induced from the nanoparticle into the molecule. Okay? And then we add up the polarizability of the nanoparticle isolated, and we give this to be the total response of the system. Okay? So this gives a hybrid approximations to the total polarizability of the total system, coupled with sort of if you would have treated everything quantum mechanically. Okay? Which means we have this additional contribution, okay, that comes from this environmental polarization. Okay? So this is essential, because if you don't include this, you won't get this e to the fourth behavior. That's essential for describing the Raman scattering. But a major problem, okay, of dealing with these systems is that, one, we have our metal nanoparticles to be very large, okay, and then we also have the molecules that is exceedingly large, okay. And so in this case here, we're just looking at purity molecules sitting inside this covered with molecules. So to do this simulations, right, each of these nanoparticles is about 3,000 atoms in each of these. And there's a 15,000 water molecules, which means the classical response equations that is necessary to solve these systems becomes very large. Okay? And this actually becomes the bottleneck in these simulations once we do the response calculations. They start to take longer time than actually solving for the QM. So to really speed up this, we have implemented two things to really make this fast. The first is that we can read the local fields. Okay, so it only depends on the metal nanoparticle. We can sort of pre-calculate them, which saves a lot of time when we deal with the Raman spectrum, where we have to calculate the local field for many different vibrational modes. For this case, we can just read them in from file. And the second thing is we've done is introduced what we call local dim for the image field effect. And it's basically just a hard cutoff, okay, considering all dipoles within a certain radius of the center of mass of the molecule. And we can show that if we use a fairly generous cutoff radius of 50 Bohr, we can reproduce the full spectrum of these molecules. Okay, but it actually reduces the dimensions of the system drastically. In this case, this is only for a single particle under the surface, but we can show that we can reproduce the full spectrum using this reduced system. What this actually does, it allows for the image field effects to be solved using in-memory solvers rather than using linear algebra iterative solvers. Okay? So this leads to a huge speed up in the set of equations, and really essential when you deal with these very large dim systems. But once we've done that, then we can actually simulate spectra that are now reached over many different conformations of molecules. In this case, we do about 25 to 50 average over that. So what you see in black is the source of the molecules in solution, and in red you see the solutions from a single Raman molecule inside this. Multiplied with 10 to the 7. So we see a large enhancement that again comes from this local field, but it's strongly perturbed by the solvent molecules. And we can show this again, that if we consider the local field around the presence of the molecules, the black dot on the left represents the center of mass of the pyridine. And once we look at the molecule in solution, we see that the field is highly inhomogeneous, and it is centered much strongly around the position of the pyridine. Okay, so the solvent molecule sort of perturbs the local field and enhances it in the presence of the molecule. So it creates an additional enhancement, okay, that is comparable to what typically describes as the chemical effect in surface. Okay, so the solvent effect modifies the local field and needs to be treated at the same level of theory, okay, to really describe these systems under these conditions. Okay. So the enhancement is stronger in solution than in vacuum, okay, and this inhomogeneity of the field is more important than the solvent. Okay. So we really need to describe this when we're looking at surface-enhanced scattering. Okay, so the last example I'm going to show you okay, has to do with modeling tip-enhanced Raman scattering imaging. Okay. And so tip-enhanced Raman scattering sort of is combined a surface-enhanced Raman scattering with a scanning probe microscopy technique. So this means you get sort of the spatial resolution that you get from the probe scanning probe, and again with the chemical specificity that you get from source. Okay, and so people have shown that you can generate images of individual vibrations on a single molecule that sits on a surface under these high conditions. Okay. And so what you're seeing here is Raman spectra, okay, rastered over the dimensions of the molecules. What you're seeing is Raman images of an individual molecule as you're scanning over this molecule with the tip. Okay, one can show that you can generate vibrations that looks like they correspond to different vibrational systems, okay, of a molecule. Okay. And so my group has been interested in actually looking at this and trying to understand what these images actually mean, okay, and how do we actually model them. And so the nice thing about this DIM-QM model is that it treats the nanoparticles atomistically. Okay? And so in principle, we could just take these calculations and then scan over the molecule and calculate the Raman spectrum in each positions of these molecules. And since the coupling of this electromagnetic field is done self-consistently, we should be able to generate these type of images. And this is in fact what we have done and demonstrated that you can do this. And so advantage, okay, of this DIMQM is that as long as you define your geometry, okay, the rest is sort of just scanning over the molecules and generate these, okay, which means you have an actual description of the interactions between the near field and the molecule. The problem is that they're still very expensive, okay? So for each point on the scanning, you have to calculate the surface-enhanced Raman. And so typically, if you generate these type of images, we typically run 5,000 calculations per normal mode of calculating the Raman spectrum. So these are very, very expensive calculations, even taking into account that the nanoparticles is treated classically. The second thing is, since the near field localization, which depends strongly on the geometry of the junction, is determined exactly by how we define our DIM system. Okay? Meaning that to describe different near field localizations, we have to change the geometry, the configuration, okay, of our nano junction, which becomes very time consuming, especially since we don't have almost no information about how the near field actually looks like in the experiment. Okay. And so what we've done instead is trying to come up with a simpler model. Okay. And so I'm going to again explain this using what we're going to call the Raman polarizability density. Okay. So if you think of the Raman polarizability density, is the change in the electronic structure due to the vibration and due to the external vibration. This was basically that electron density that we perturbed or partitioned into the atoms and the bonds. Here we're just looking at the full spatial distribution of this. When you plot it here, is the Raman density, okay, of a benzene molecule. So this turns out to be an out of plane vibration of a benzene molecule, this new 6 mode. This is a Raman inactive mode. Okay. And the way to understand this from looking at the Raman density is, again, that the color here, the blue and the yellow, corresponds to density changes with opposite signs. Okay, the Raman scattering is then integrating over this density over all space. Okay, and there's roughly equal amount of blue and yellow, and hence you will see that this Raman cancels. Okay, there's a little bit of additional blue here because the molecules on the surface, a little bit of the density has been changed due to the surface of the wall. You get a Raman intensity that's near 0 due to this cancellation. Okay, so this gives you the traditional surface selection rules, okay, where you probe the full density over the molecule, and also what you would get if you probe an individual molecule in gas phase or solution. So this is the traditional Raman selection rules, can be understood by looking at these. What happens when we have a nanoparticle, okay, is that we need to consider the density being perturbed by the local field. And so in principle, we have to consider this nonlinear response, okay, due to the perturbed field at 2 different positions. Okay, so this is the thing that is solved self-consistent in DIMQM, okay? And why this is a very expensive calculation, because you have to solve for the self-consistent polarization for every single position that you're looking at. Okay, what we've done instead is we're going to make it a local approximation to this, meaning that we're going to say that this nonlinear response really is only dominated by the response right where you have the tip. Okay, so that means that we can actually approximate the fields to be independent of position. They only depend on where the tip is. Okay, and we can rewrite this in terms of the induced density of the free molecule modulated by these electromagnetic fields. Okay, so this decouples solving for the induced charge density. We're only going to solve that once, okay? And then we're going to modulate how this changes due to this electromagnetic field on these positions in here. Okay? This means that the density is not solved self-consistently. Okay? This is the approximation that we're making, but we're only thinking about this that is perturbed locally rather than globally. Okay? And so this leads to this, what we're going to call local Raman density. And so this is what's illustrated here. And so in tip-enhanced Raman scattering, the simplest way of thinking of what's happening is that you're looking at this Raman density that comes from the free molecule, but you're only looking at a region of space that's determined by this field localization. Okay, so this leads to this idea that we're going to call local integrated Raman possibility density. Okay? We can show that this corresponds to a good approximation of what you would expect from a full DIMQM calculation, because the field is very strong in this region where the field is localized. And then when you're changing over this, you're only probing the small volume rather than the full density, and hence you can break the traditional selection rules that you actually see in surface-enhanced Raman. And then you're rastering over this, your images corresponds to this locally integrated electron density. So using this approach, we've been able to explain a large number of molecules that you said, and because again, this boils down to, again, of simulating instead of having the self-consistent polarization at every single point. All what we need to model is, again, the response for the free molecule, and then we can locally integrate to generate these images. So that leads to much larger effects. We can see that we can get a good representation of the TERS spectrum and looking at this model. So this is, again, this H2TBPP molecule, this porphyrin molecules on here. Okay, that sort of planarizes onto the surface, okay, and changes the structure of this, okay, and we can capture that using this locally integrated method. Okay, but more importantly, we can explain why these images actually appear. So as we're moving the tip over this, we're probing the local vibrations, which is localized in certain regions of this, and we're integrating over this. And so what you see in the signal, okay, is again these small density changes that happens localized in the molecule when the tip is near that, and that's what's reflected in this. And the reason these molecules all look similar is that most of the vibrations is actually in these wingtip groups that are sitting on the different ring itself. Okay. And then we can see that these are actually fourfold degenerate. Once we sum them up, we'll generate these images that look like these donut-shaped molecules that you actually see experimentally in doing this. So hopefully I've shown you sort of three aspects of modeling of the surface-enhanced Raman scattering using tools that are implemented in the ADF packages. Both this idea of generating the Raman bound model that allows us to interpret the different mechanisms using full TDDFT, incorporation of solvent effects into the simulations, accounting for the changes to the localized electromagnetic field, and then simulations of these high-resolution single molecule vibrational images using tip-enhanced Raman scattering, for accounting for the highly localized field due to that atomic structure of the tip really leads to these changes of the selection rules. So before I end, I will make sure to acknowledge the people that have actually done all of the work. So this is work that we've been doing over a large series of years, and all students have been able to contribute to that, funding from NSF. Thank you for the attention. I'll be happy to answer any questions.